Hey, good morning. So today I'm going to begin on the second chapter of chemical bonding, which is called Bonding 2, it's chapter 9. And we're going to begin with a discussion of molecular shapes. Now in chapter 8, what we did was we essentially just focused on Lewis structures. When you think about it, we had this idea that electrons form pairs between atoms, and we called those pairs of electrons chemical bonds. And we could have single bonds, we could have double bonds, we could have triple bonds, we could have lone pairs. What we're going to look at here are several different ideas about chemical bonding in this chapter. So it's a little bit more advanced, and it's all based on our familiarity with the Lewis structures. So in this chapter, there's even more work with Lewis structures, but really just as the starting point for our discussion. So one issue that arises with Lewis structures is its inability really to predict the shape of a molecule. So for example, if we draw the Lewis structure for water, two single bonds, one to each hydrogen with the oxygen at the center and two lone pairs on the oxygen, there really isn't any strategy we can use with Lewis structures to predict the shape of this molecule. So what we're going to do is we're going to introduce something called the valence shell electron pair repulsion theory, which is called VSEPR. It's VSEPR, but we pronounce it VSEPR just to make it easier to say. And it's essentially a model based on, it's a theory based on what it says it is. We're going to consider the valence shell electrons. They're in the form of pairs and they repel each other. The electron pairs repel each other. So first of all, to begin, what we want to do is we want to identify what are called electron groups under this theory. And this actually will help us for a couple of the other ideas that we cover in this chapter. So we're going to call these electron groups. Okay. An electron group is a lone pair, right? And remember, we represent a lone pair like this. So that is considered an electron group. A single bond between two atoms is also considered an electron group. Now, what is important for this idea of the electron groups is to recognize that a double bond is also considered one electron group, not two electron groups, but one, right? So we're counting essentially electrons in a particular region of space. So a double bond has two pairs of electrons, but they're occupying approximately the same region of space. So we consider a double bond one electron group, and the same goes for a triple bond. So a triple bond has three bonds, right? Three pairs of electrons, but that's considered one group. And what we do in VSEPR theory to begin with is we count electron groups around the central atom. That's the first step. In particular, the central atom. Okay, so we count electron groups around the central atom. So let me show you a couple of examples just to kind of get us started on that. A lone pair, single bond, double bond, triple bond. We count them all as one electron group, and then we count them around the central atom. Okay, so let's imagine water again. Let's come back over here to water. It's pretty simple. So we're just considering the central atom. This is the central atom here. And we just count up. It has two lone pairs. and 2 single bonds. Okay, so that's 4 electron groups. Simple as that. Each lone pair is one group, each single, double, or triple bond is one group. Add them all up, you get the number of electron groups. Okay. Generally just around the central atom. If there's more than one central atom, then we would do it for each atom separately. Okay, so here's another example. That's formic acid. Let me finish the Lewis structure, make sure I got that complete. So let's consider from the perspective of this carbon, how many electron groups it has. Well, no lone pairs on that atom, but it does have a double bond. And it does have 2 single bonds. So that's a total of 3 electron groups. Okay. Here's one more. This is called sulfur hexafluoride. It's an interesting molecule. Very good at putting out fires. Okay, so again, from the perspective of the central atom, the sulfur is the central atom. There are no lone pairs, no double bonds or triple bonds, but there are a total of 6 single bonds. So that gives us 6 electron groups. You may see out in the literature electron domains. I'll put that in parentheses. So some textbooks use, instead of the word group, they use the word domain. It means the same thing. Okay. All right. So why is that important? Well, it comes back to the idea of how we defined this model, or how we titled this model. Valence share electron pair repulsion theory. So we might actually, the better name for it would be a valence shell associated electrons repulsion theory. What the main idea here is that electron groups repel each other. And move as far away as they can from each other. Okay, so the idea would be this, that if you had an atom and it had 2 single bonds, that's 2 electron groups, right? They would move away from each other. Essentially, it's electronic repulsion is the idea, right? Electrons are negatively charged. So they would move as far apart as they could. And if you had 2 electron groups, they would move, that's as far apart as they can get. If you had, 3 electron groups, so notice that I'm using a single, a double bond, and a lone pair, just to, those are all 3 of those are examples of electron groups from the previous discussion. These would move as far apart as they could. So like, this one might move over this way, this one might move over there, and this one might move over there. And then they would be something like this. See how I'm drawing them as far apart as I can? You end up with like a little triangle. So when I say they move far apart, what I mean is in an angular sense, right? The angles are maximized. So it maximizes angular, angular distance. Okay. So if you had 3, they would move like a little triangle. That's about as far apart as they can get. Now, there are problems with this model. There's problems with this theory, but it's very simple because all you got to do is count up the number of electron groups and then just remember the geometry, how far apart they would be, like what is the shape for having certain numbers of groups around a center, right? So let me go through this and I'm going to show you sort of the results. Okay, so the results are, I'm going to use a notation A, B, 2. Okay, A, B, 2. Now, in this notation, A is the central atom, and B are surrounding atoms. Okay, this makes the following, in this table, the following assumption. There are no lone pairs on the central atom. Okay, no lone pairs on the central atom, so only just surrounding atoms. And so what happens is when you have one central atom and 2 surrounding atoms, you get a straight line, which is called linear. So that's the name of the shape. Then you have an angle associated with it. It's 180 degrees. And now what I'm going to do is I'm going to show you how that angle is measured and what it looks like in terms of space. Okay, I'm showing the angle here. The angle that we're talking about is the angle between one bond between the central atom and one of the surrounding atoms. And then you sweep out an angle over to the next closest surrounding atom. So you start between the central atom and one of the surrounding atoms, and you sweep out an angle to the next closest surrounding atom. And so that would be 180 degrees, right? Notice that's half of a circle, right? You're going half of a circle. It's a semicircle. So that would be 180 degrees. And it's called linear because it's a straight line. Okay. It's 2-dimensional. It's 1-dimensional, actually. So if you have a linear molecule, it's actually 1-dimensional. And we'll look at examples of molecules like this. An example is CO2, carbon dioxide. Okay. Now, the next one is AB3. Again, the assumption in this list is that there are no lone pairs on the central atom. It's all bonds. And we'll talk about lone pairs later. This one is called Trigonal Planar. Has 2 words. Now, the names are somewhat variable. For some reason, chemists have not come up with, it has to be called this name. They're just different names that they give these things. So sometimes you'll see triangular planar. Trigonal is the more common name, okay? The angle here is 120. And it's like that second one I just showed you. Okay, so you got a central atom, 3 surrounding atoms. Now, why is it 120? Well, it's a third of a circle. So going from this atom to this atom, sweeping out an angle there, that would be 120 degrees. It'd be another 120 to here, and another 120 to here, which would give you 360, right? Which is the angle, that's sweeping out an entire circle. An example of this is, there are many examples, but boron trifluoride. By the way, the B here does not refer to boron. It just refers to a second atom. So sometimes you'll see AX2, which, arguably that's maybe a better notation to use because there is no symbol X in the periodic table. AX3, AX4, whatever, so forth and so on, okay? So a little triangle, triangular or trigonal planar. The next one is what happens when you get 4 surrounding atoms. Again, no lone pairs on the central atom. This one is called tetrahedral. And the angle is 109.5 degrees. Now I want to separate this. I came down a little bit too much there. So let me draw lines through these just so that you can see they're separate. Okay, this is called tetrahedral. It's 3-dimensional. Now, what happens is when it's 3-dimensional, there are different ways to draw it. So typically, or one way, is to draw a little angle here, and then actually do it like that. I'm sorry, let me fix this up a little bit. I'm going to draw it on this side. Then come out like this with a little wedge. I'm going to make it solid just so you can see that's a wedge. And then a little dashed line there. So these are your surrounding atoms, attachments. They're essentially, you think of them as attachments. Okay. The common molecule for this structure is methane, CH4. Okay. Now, this notation, which is the wedge notation, the wedge dash notation, this is 3-dimensional. Okay, so this one's a little tricky. So what I want to do is I want to show you an actual structure of this. Let's take a moment here just to put this together so that you can see it. Okay. So again, the A is the central atom. So in the case of methane, it would be a carbon atom. And then there are 4 attachments that are as far apart from one another as possible. So think of these as the bonds or the electron groups. See how far apart they are? See how it's 3-dimensional? It's not 2-dimensional, right? So you might have predicted it would be 90 degrees, 180, 120, and then 90, but no, it's 109.5. The geometry works out to that angle. And then the attachments to the bonds of the surrounding atoms are just going to reflect the angles of the electron groups, right? So the electron groups move as far apart as they can. That's electron pair repulsion. And then the attachment points of the atoms are right here. So that's why CH4 is this tetrahedral arrangement, okay? So it's kind of like a pyramid. Now the notation is essentially what you have to do is you have to show a 3-dimensional object in 2 dimensions. So what you do is, you have a little bent here. See how that's bent? And that would be representing, this right here, right through there. That's the bent. But then you have to have one coming out of the board, and that's the wedge. That's the little solid wedge right here. So this is coming out of the board, and then you have to have one that's going away from you. So coming towards you, going away from you, right? But it's not coming straight out at you, and it's not going straight back, right? If it were, it would be obscured by the central atom. It's just coming out a little bit at an angle here and a little bit at an angle there. So, there's different ways to draw these, but this is probably the most common form. So this is coming toward you, and then this is going away from you. Okay, and the assumption here is that if you rotate it, you can rotate it, it might look a little bit different too, but it's essentially the same structure. Okay, so that's the first one that's 3-dimensional. The next one is also 3-dimensional, AB5, right? See the pattern here, AB2, AB3, AB4, AB5. If you only have 2 atoms like AB, that would have to be linear because you only have 2 atoms. So this is called, again, sometimes the names are variable. This is called Trigonal Bipyramid most commonly. But you might see the AL at the end. And again, you might even see triangular, So this one has 2 angles. It's 120 and 180. And I'll show you why it has 2 angles. I'm going to try to draw this little guy 3-dimensional. Okay. So I'm using this wedge dash notation on both sides. and then I'm doing up and down. Okay, so notice how you got, well, I just did 6. I'm so sorry. I did 6. I was a step ahead of myself. There we go. Okay, so this one's a little trickier. This one, again, is 3-dimensional. Let me see if I can find the correct little guy here. I may not be able to find one very easily. Just got one, it's got 4. Here we go. There's 5. Okay, so let me just pop these off. Okay, one way to look at this is that you have 3 electron groups in the center of the central atom. These are often called well, by the way, that looks like trigonal planar, right? So these are called equatorial positions because you think of the central atom, you can think of the central atom sort of like a globe. So it has an equator at the center, and then it has poles, right? So you might think these would be called polar, but we don't want to use that word because that has a different connotation. So we use axial for the ones on the top and the bottom because they're on the axis. And axis. Okay, so I know I have more of these. There we go. So now we've got 5. I jumped ahead and did 6, right? But this is just 5. Goodness, there we go. It's hard to get these in there sometimes. Okay, so you got 3 in the center, and notice that's like trigonal planar. But we also have these 2 top and bottom. So the equatorial are at the center, the axial are top and bottom. And the 2 angles is because we have 2 angles, right? There's an angle here, which is 120 between the equatorial atoms. And then you also have from the top to the bottom, like a linear, right? So really it's a superposition of 2 different structures. It's trigonal planar and linear. So 180 for the linear part, and then 120 for the trigonal planar part. So that's why you got your 2 angles there. Okay, and then an example of this is phosphorus pentachloride, PCl5. Okay, and then the last one of this group, okay, now remember these ones in here, those are called equatorial. And then this is called axial. Okay, the last one, AB6, we're not going to go any further than that with this group. This one's called octahedral. Even though octahedral sounds like it starts with an 8, it sounds like 8, right? Octa, 8. Well, the 8 comes about. I'm going to show this instead of having surrounding atoms. I'm actually just going to put the electron groups sort of like this, just so you can see them. Sorry for the different colors. I just don't want to take the time to look for the exact same color for each one. Okay, did I get it? Oh, I used the wrong one. Sorry. I meant to use yellow. 1, 2, 3, 4. It's organized better. Okay, there's 1, 2, 3, 4. 5. Again, I can't find all the same colors, so I'll just use different colors. So instead of having a single bond and then atom at the end, I'm just putting the actual electron groups, right? So when you have 6 electron groups, you get this arrangement. This is octahedral. Why is it called octahedral? Because the geometric shapes, the Greeks essentially name them based on how many faces there are. And there's 4 faces up here and then 4 down here. So that's 8. So it's octahedral. But there's 6 attachments. Okay. So octahedral is 90 degrees. Why 90 degrees? Well, From here to here is only 90 degrees. Okay, from here to here is 90. From here to here is 90. From here to here is 90. So it's considered 90 degrees. Now this one, again, we've got a lot of them. So we're going to have 4 on the equatorial positions at the equator, and then 2 axial positions. So you got AB6. So the sulfur hexafluoride is an example of that, SF6. Okay, so those are your 5 basic structures under VSEPR theory: linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. Okay. Now, in practice, what you do is you draw the Lewis structure, and if you find that the Lewis structure, there are no lone pairs on the central atom, then you just use this table right here. It's AB2, no lone pairs, it's linear. AB5, no lone pairs, it's trigonal bipyramid. But notice you got to draw the Lewis structure to find out if there's lone pairs. And I'm going to cover what happens if there's lone pairs on the central atom separately. That's a separate table. I'm only going to go over a couple of them, but we'll cover them separately. Okay. All right. So that table, I would memorize it. AB2, AB3, AB4, AB5, AB6, linear, trigonal planar, tetrahedral, trigonal bipyramid, octahedral, 180, 120, 109.5, 120, and 180, and then 90. And then you don't have to memorize the examples, but you also should practice drawing them, drawing the arrangements. Okay. So let's take a look at an example. I'm going to come up here, and I think I have one open here. There's one. And then let's share this one. Okay, so predicting the arrangement of electron groups around the central atom. How many electron groups are found around the central iodine atom in this structure per iodate? Notice 1 electron group means 1 lone pair, or 1 single bond, or 1 double bond, or 2 or 1 triple bond, right? Triple bond is not 3 electron groups. What phrase best describes, and then you're going to select, okay, the electron groups. You're just trying to figure out what the arrangement of electron groups are. So per iodate, is IO4 minus. Okay, so how do we draw the Lewis structure? Well, we put the iodine in the center, surrounding them by the oxygen atoms. Of course, we realize that it's an ion, so we use our bracket notation, right? Then we count up the number of electrons. Now, iodine is in group 7A, so there's 7. Oxygen is in group 6, but there are 4 of them. And then it has a negative charge. So 24 plus 8 is 32. We've already used 2, 4, 6, 8. So we've got 24. Now I'm going to give you a little tip here in terms of VSEPR theory. I could make the argument that we need to have more bonds to the central iodine atom, and that's absolutely true. I don't like this Lewis structure. This is the one that Alex will actually show you as being correct for this problem. We're only interested in electron groups around the central atom, and a double bond is the same as a single bond in terms of counting the electron groups. So that means it doesn't matter whether we form a second bond to one of the oxygens or to 2 of the oxygens. I would argue probably 2 of the oxygens form a double bond, maybe even 3. But that's okay. You could do that if you want to get the formal charge closer to 0 for the iodine, and that would be perfectly fine. But it doesn't matter in terms of the VSEPR theory. All we need to know are how many electron groups there are, and a double bond is the same as a single bond. So all we got to do is count them up. 1, 2, 3, 4. There's 4 electron groups, right? And if you have 4 electron groups, that's tetrahedral. Which is 109.5 degrees. Now, they're not going to ask you to draw this, but I'm going to do it anyways. Okay, there's your arrangement, right? 109.5. I drew that as a bent bond. That's terrible. I'm being pretty sloppy here. Sorry. And then there's your wedge, right? Remember, the wedge is coming out, the dash is going into the board away from you. And then this, if it's a straight line, if there's no wedges, then it's like in the plane of the board, the paper that you're drawing in. Okay. So there you go, tetrahedral 109.5, and there's 4 electron groups. So that problem is just asking for the number of electron groups. Let me show you another one. Azide ion, N3 minus, right? The azide ion, N3 minus. How many electron groups surround the central atom? Again, VSEPR is all about the central atom and then what's the structure. Okay. So I'm going to draw the Lewis. So notice you get more practice doing Lewis structures with this whole theory. So 3 nitrogens, we're only concerned about the central atom in terms of the number of electron groups. Nitrogen is in group 5A, and there are 3 of them. And then there's a negative charge. So you got 16. We've already used 4, so that gets you down to 12. So in general, what you do is you get the central atoms up to 8. Okay. So that gives you 16 electrons. The whole thing is negatively charged. Well, that's interesting. Okay, so this nitrogen atom doesn't seem to have enough electrons, right? Doesn't have the octet rule. So what I'm going to do is I'm going to push a pair over. And that's going to give me, let me just close this out. I'm sorry about the noises. This is going to give me a double bond here. Right? Now the nitrogen atom is at 6, but we need to get it up to 8. So now you have a choice. You could do another pair over here to get a triple bond, or you could do a pair on the other nitrogen to get a double bond. And it turns out either of those are reasonable. They're just resonance structures. So I'll do the one on the right, and you'll get 2 double bonds, right? So I'm just going to push this guy over here. And there you go. Now, again, if I had done the triple bond on the left and a single on the right, or a single on the left and a triple on the right, you still end up with 2 electron groups. Remember, a double bond is an electron group. So is a triple bond. So it doesn't matter if you have a triple and a single, or a single and a triple, or 2 doubles. It's still 2 electron groups. There are no lone pairs on that central atom. So there are 2 electron groups. So that would be your answer. And if you have 2 electron groups, that's linear, right? Because there are 2. So the actual arrangement would look like this. Linear. Okay, 180 degrees. Memorize those numbers. 180 is linear. Okay. Interesting, right? And it comes down to the fact that there's no lone pairs. If you had a lone pair on the nitrogen in the center, that would change things. We're not worried about lone pairs on the surrounding atoms, just the central. The VSEPR theory is based on the idea of a central atom surrounded by electron groups. The atoms essentially attached to these electron groups, and so they're going to reflect the structure of those electron groups. Okay. Okay, here's another problem. So let me stop share here. Let me share this one. Different, interesting problem here. This gets, so the software engineers put together something they thought was fun. You want to identify a molecule with one central atom in its 3D shape. Okay, so if you look at this shape, what does it look like? Does it look linear? It's not linear, right? It's not trigonal planar. It's not tetrahedral. It's none of those shapes I told you about, right? So that's an interesting issue there. This one has a different shape than any of the ones that I gave you. So what I need to do is I need to give you a little bit more information because there's some shapes I haven't gone over. So let me do that. I'm going to stop the share here. I'm going to come up here and show you some additional shapes. And these additional shapes are what you get when you have lone pairs, PAIRS, on the central atom. Okay, that's the difference here. So those first 5 that I gave you, linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral, those are all the cases where you have no lone pairs on the central atom. Now I'm going to show you a couple that have lone pairs on the central atom. Okay. So the first one, I'll number them, is where you have 2 surrounding atoms and you have either 1 or 2 lone pairs on the central atom. So we're using the notation E is a lone pair on the central atom. Okay. Now, what happens when you have 1 or 2 lone pairs on the central atom is those lone pairs take up space. So let me show you what I mean by that. So imagine we have, a central atom with 2 surrounding atoms. So let's make that nice and simple. That's our linear arrangement, right? AB2. 2. Oh, that does not want to go in. There we go. Okay. Sometimes you have to force these things in there. Okay. Central atom, 2 electron groups, 2 surrounding atoms. That's your linear. But what happens is when you have a lone pair on the central atom, it is going to take some space as well. Okay. It's going to take up some space. So what will happen is, okay, let me just make sure. I'm going to stop screen here. Okay. So what's going to happen, you have the central atom, 2 electron groups, 2 surrounding atoms, that's linear. Now, what happens is if I add a lone pair, and I'm going to represent the lone pair using this. This looks like an atomic orbital. So this atomic orbital is going to come in here and take up some space too. This atomic orbital will push these 2 electron groups away from it, right? It's going to push them away. And so what you end up with, if I can find, here we go. There you go. You end up with this. See what that electron pair did? That lone pair. The lone pair is right there. Here's your 2 surrounding atoms. It essentially pushed them away, so it's no longer linear. Now we have this shape right here. Look at it. That's not linear. So what do we call it? These 3 atoms have some sort of angle. We call it bent or angular. Some people call it angular, but generally it's called bent because everything's angular. That's a crazy name, but whatever. I've seen it out there. We call this bent. It's just a bent shape. Okay. So that's what you get when you have AB2 E1 or AB2 E2, 2 lone pairs, right? It's bent. And the angle is 104.5 all the way up to 120. There's a range of angles. What happens is if it's E2, it tends to be on the smaller side. And if it's E1, it tends to be on the longer side, 120. And it looks something like, oh, water, by the way, is an example. And it looks something like this. Let me draw the picture down here. A, B. Okay, does that make sense? You got two surrounding atoms, which means two electron groups, but you also have one or two lone pairs, which push them away. So it's not 180 anymore. It's much less than 180. It's something like that. Okay. So let's take a look at that one. So that one right there, that's an important one right there that you kind of need to know that one. One, you know, either 104.5 or 120. But in this particular problem, here's what happens. They give you the picture. So really you have to recognize that shape. Now, I can't actually modify that, but you can. You can move it around and stuff, play with this to rotate it and all that. They're giving you the shape, but recognize that's bent, right? So you're going the opposite direction. We're not going, here's the Lewis structure, predict what the shape is. They're giving you a picture of the shape and you have to figure out what's going on in terms of its electronic structure. But here's a couple clues to this. You got one central atom and then you got two surrounding atoms. Now I would argue that these are all the same color, so you would think they were the same element. So if you look at this N3 minus, possibly, right? H2O2's got 4 atoms. That's not possible. There's 4 atoms. There's only 3 here. CO2 has 3 atoms, and then BRCN has 3 atoms. So, you know, 3 of them seem possible in terms of the number of atoms. So what I'm going to do is I'm going to draw the Lewis structure. For the BRCN, the carbon is most likely at the center. For the CO2, the carbon is at the center. And then here, actually, didn't we just do N3 minus and that came out to linear? Let's see. Let's go through these. Okay. So the molecule looks like this, or the structure looks like this. It's bent. Okay, so we have options: BRCN, CO2, H2O2. This one's not possible because it's got 4 atoms. This has 3 atoms, most likely. And then this is N3 minus. Now we just did N3 minus, right? Let's do that one real quick. Remember how we showed that that one was linear? Because it has 2 electron groups. So that's not one of the options. So forget that one, forget that one. What about CO2? Okay, there's CO2. Carbon has 4 electrons, it's group 4A. Oxygen, there are 2 of them and they're in 6A. So that's 16. We've used 4. So I'm going to put them on here. Okay, minus 12, there's your 0. Sure, put a double bond in there to get it up to the octet rule. But in fact, you don't even have to get that far, to be honest with you. Even if you just left them as single bonds and didn't even do the octet rule, at least you got octet on the surrounding atom. But in any case, either way, you're going to have 2 electron groups, not 3. Okay, so that means it's linear. So that's no good as well. So maybe BRCN is going to be one. None of the other 3 work out. H2O2 because that's the wrong number of atoms. But let's do BRCN. Bromine has 7. Carbon has 4. Nitrogen has 5. 7 plus 9 is 16. We've used 4. That gives us 12. So we put 6 on each of the surrounding atoms. Okay, same situation, just like CO2 and N3 minus. If you start getting that carbon atom up to a double bond on each side, just to get it up to 8, right? We want that carbon to have 8 electrons. Okay, there's still only 2 groups around the central atom. That's linear. So no, none of them in that particular case are bent. Okay. Yeah, there you go. None of them. Interesting. Okay. So let's try another one. Okay. Same idea. They're going to give you 4 formulas. You're going to have to draw out the Lewis structures, just to see if they work out. Now notice you've got 1 central atom and 4 surrounding atoms. So any of those that have 3 or 5 surrounding atoms are not going to be any good. So that first one, NH3, you can get rid of that first one, NH3, right off the bat. It only has 3 surrounding atoms, so that can't be possible. But CF4, CH4, and BrF4 minus, those all seem like possibilities. Okay, so let's take a look. Now, by the way, that's tetrahedral, right? That's one of the structures we did look at. That's your, where you got this sort of bent here, and then it comes out and goes in. That's your tetrahedral arrangement. So really, we just have to figure out which one's tetrahedral. Okay, so let me show it to you again, just so you see it. Okay, so that's what they're showing you in terms of the structure. It really looks like AB4, right? No. We'll come back to that. So here's our options: NH3, CH4, CF4, and then BrF4 minus. Okay. All right, so again, we can omit that one. It doesn't have the right number of surrounding atoms, but let's try CH4. So CH4 is, it's a candidate, right? It's possible that that's a tetrahedral. Okay. Well, let's do our Lewis structure. Carbon has 4 valence electrons. Hydrogen has 1. So that's 8, but we've already used 8. It's all done. Octet on carbon, duet on hydrogen. This one's done. Okay. So now how many electron groups? You got 4 electron groups. And we said 4 electron groups was tetrahedral. Right? So definitely, there we go. There's one. That previous example, none of them were good, but this one's good. CH4 is good. It's got 4 electron groups, 4 surrounding atoms. That looks good. What about CF4? Okay, well, carbon has 4 valence electrons. Fluorine has 7. So that's 32. We've used 8, so we got 24. Now notice, again, the carbon already has 8 electrons, so no need to do any bonding in addition to that. Just put 3 lone pairs on each fluorine. That'll give you your 24. So again, 4 groups, right? A single bond is a group. There's 4 groups there, so that's tetrahedral. Good. So that one is also tetrahedral. So you're looking at the picture, you're looking at the model, identifying what shape that looks like. Then you're going through the Lewis structures and determining the VSEPR structure. BrF4 minus. Now that one's a little interesting. BrF4 minus takes a little more room here. So you got bromine, 4 fluorines. This one might be an expanded octet. It might actually have lone pairs on the central atom. And so just like that bent one that had lone pairs on the central atom, this one we have to consider. So bromine has 7, fluorine has 7. So that's what, 28, 36. We've used 8. So we've got 28 left. Okay, so here's what's going to happen with this one. You're going to get your 6 in the form of lone pairs on each fluorine. So there's 24, but you got 4 left over. They're going to have to go on the central atom. Okay, so there you go. That's on the central atom. So notice you've got 6 groups on 6 electron groups on the central atom. A lone pair is a group, right? Okay, well, that's octahedral. So in fact, what happens is the arrangement of the electron groups are octahedral. That's true. But the name of the structure is not based on the electron groups. It's based on the attachment of atoms. So that's why, you know, NH3 was not tetrahedral, because even though it has a lone pair giving it 4 groups, it doesn't have 4 atoms surrounding the central atom, nitrogen. So this one is not tetrahedral because it has 6 groups, not 4. So this one is no good. So you can cross that one out. Okay. Now, what you're seeing is that some of them don't seem to fit the, you know, the general kind of scheme, right? This one has 3 atoms. This one has 4 atoms, but it has 2 lone pairs. So that second set, there's a second set of structures. I went over the first one, which was the linear through octahedral. Now what I'm going to do is I'm going to go over, just put down a list of these just so that you have them. There we go. Let me go back over here. So here's our second group. Okay. All right. So we had the first one, which was bent AB2, E1, or AB2, E2. This was bent. And again, I gave you a range, 104.5 to 120. Okay. Now in Alex, from what I recall, they actually say, hey, just use the basic 109.5, which is the same as tetrahedral, and that's perfectly fine. So you got an atom in the center, and then you have a bent arrangement, 2 surrounding atoms, right? AB2, 2 surrounding atoms with either 1 or 2 lone pairs. They just say, just go use 109.5, which is fine. The next one is AB3 with 1 lone pair. And this is called Trigonal Pyramid. And then again, sometimes people put AL at the end. This one is 3-dimensional. Looks like a little pyramid, okay? And the angle, again, is typically 107 degrees, but Alex will tell you to use 109.5. They're saying just use the basic angles, which is the tetrahedral angle, right? Okay, so the lone pair is what makes it not trigonal planar. The lone pair is what makes it not linear. Now here's another one, AB4, E2. And this one is called square planar. Okay, and the angles are 120. I'm sorry, 90. So that you have the central atom, okay, and then it just makes like a little box, like a square. It's a square and it's flat. So your B's are right here. Okay, so using this notation here, you would just put a little dot there to represent the surrounding atom. I'm just trying to make that consistent with Alex. Okay, so what happens is the reason it's 90 degrees is it's really octahedral. Each of these lone pairs takes up a space, one up here and then one coming down, right? Those are your lone pairs. But we don't draw them in when we draw the structure, when we draw the, the shape of the molecule. Okay. I think I can close this, right? There we go. To close the right thing. Okay. So there's another one. There is AB3, E2. Okay, this is called T-shaped. Okay. And the T-shaped is sort of strange. You got the central atom here. And then it comes down like this. See why it's called T-shaped? So AB3, and then you got two lone pairs, which take up two of the positions. This is essentially what you get with, you got a total of 5 electron groups. So it's really kind of like trigonal pyramidal, but 2 of the groups are lone pairs. Okay, and these are 90 degrees. Okay. There's another one called Seesaw. I'm not going to go over the Seesaw, but these are the 4 pretty common ones that have the lone pairs, right, in the central atom. So 2 groups. So really what you do is you look at the formula. Oh, 1 central atom, 2 surrounding atoms. Okay, well, that could be linear, or it could be bent, right? Those are the 2 that are AB2. So then you draw the Lewis structure. If it has lone pairs on the central atom, then it's bent. If it doesn't have lone pairs, then it's linear. Okay. If you have 1 central atom and 3 surrounding atoms, it could be trigonal planar, or it could be trigonal pyramidal, right? Those are the 2 structures that have AB3. Then you just look to see if it has lone pairs. If the central atom has lone pairs, then it's trigonal pyramidal, and it's 107 degrees or 109.5 degrees, and it looks like a pyramid. Okay. If it's AB4, again, it could be tetrahedral, or it could be square planar. If it's got 2 lone pairs, then it's square planar. If it doesn't have any lone pairs, it's tetrahedral. And the Seesaw is actually the one where you've got the AB4 with E1. AB4 with E1, this is the Seesaw. And then if you've got 3 surrounding atoms, again, there's another one with 3 surrounding atoms, which is the T-shaped. So if it has 2 lone pairs, then it's your T-shaped, okay? So really what you want to do is you just want to have a set, have a table with, just listing what the structure is going to be based on the Lewis structure, okay? So let me see if I can find you another example. Okay, this is kind of cool. This one's simple. Some of these ALEKS problems are really basic, and then other ones are like kind of involved. And there's no kind of pattern to like get simple, harder, harder. So use the AXE. So they're not using B, they're using X. Your textbook, I think, uses B, but ALEKS uses X. AXE, okay? Use the AXE notation to describe a molecule with a central atom, okay? So they have this SBr4, and they want you to use the AXE notation, so SBr4. So let's go through it. Okay, so the A is there's only going to be 1 central atom, so you don't put anything there, right? Because we don't put like H2O1, we just put H2O, right? So there's nothing under the A, so you just leave that blank. Now there's 4 surrounding atoms, there's 4 bromines, so we put a 4 there. Now the only issue is like how many lone pairs do we have, 1 or 2? So you got to draw the Lewis structure, right? That's how you find the lone pairs, you draw the Lewis structure. Okay, sulfur has 6 valence electrons. Bromine has 7. So that's 34, right? 28 plus 6 is 34. And then we've used 8 So that's 26. So 2, 4, 6, 8, 10, 12. Remember, you only need 8 electrons on any of the surrounding atoms. So we're not going to go any more than 8 electrons on the surrounding atoms. So that's got to go on the central atom, right? So it looks like you've got one lone pair. So that's showing the lone pairs there. So A, X4, and then E, and then, I would put a 1 there, but let me check to make sure that Alex does it the same way. Sometimes they just say, yeah, so they're using 1. So you just put a 1 there. Okay. If there are no lone pairs, they're saying put a 0 there. I guess, if there's no lone pairs. But in practice, we would just write AX4, okay? So X, those are your surrounding atoms. They call them ligands or ligands, which is, to be honest with you, an advanced term that's generally covered in more advanced chemistry courses. It's really not appropriate to use that term in a general chemistry course, but that's fine. That's the word that they're using, okay? So let me show you one more. And then we'll end this. Okay, so this is CLF3. So the A, you don't need to put anything, right? Because there's only one central atom. You've got 3 surrounding atoms, so that X is going to be 3. The only issue is how many lone pairs do you have? 0, 1, 2, or 3. I don't think you're ever going to have more than 3 lone pairs on the central atom. Generally going to have, 0, 1, or 2. But it is, I guess, possible to have 3. Okay, so Cl, let me just make sure I get the formula right. ClF3. Okay, so chlorine at the center, 3 fluorine atoms. Okay, 7 electrons for the chlorine, 7 electrons for each fluorine. So that's 28. We've used 6. We're down to 22. We're going to put 3 lone pairs on each surrounding atom to get, that'll be 18 right there, right? Those lone pairs are 18. And then we're going to have 2 more lone pairs there. Okay. So what do we got? We got A, X3, right? 1, 2, 3. And then you got 2 lone pairs, E2. That's kind of fun actually to do those, right? And then the question is, what is AX3E2? I think that's the one I told you was a T shape. They don't ask you for the shape here, but that's what it would be. Okay. And there you go. Okay, so that's a second time, actually a third type of problem. So what I'm going to do tomorrow is I'm going to wrap up this section by looking at some more examples and maybe even look at some smaller organic molecules, and then we'll get into molecular geometry and polarity as well. Okay. All right. Vesper theory. Have a great, great day.